tendency. Excellent. So in terms of the chapter 0, anybody has any question? From chapter
Professor,
0?
you don't record your lectures, huh?
No.
Okay.
But I have some videos. I'll put some videos. I'll be making more videos too on this
Yeah,
topic.
just I'm not trying to really miss anything. Yeah.
No, you don't miss anything. Just stay in touch in the class. An important chapter, I'll make videos. Actually, separate than the class. I'll put it on the YouTube. I have some video on YouTube, but okay, let's chapter 0. It's PowerPoint. All right, so we may have some question here now. Some computers, we learn about. Oh yeah, okay. Let's have some questions answer session from the chapter. All right, so I think I'll pick people. But if you don't know the answer, just say pass, okay? It's not that you'll lose points or anything like that, okay? It's just a class participation. So if you don't know the answer, just say pass. I wouldn't need anything. I won't take any note on that, okay? Just a class discussion stuff. So that's what I'll be going through, like every class, like a few minutes, just to review the previous chapters that we've been through. So it helps people that if they miss the class, then they have some chance to learn about it. And also, of course, if you've been through the class, you learn it, you review it. And this is the time you review and reflect. And if you have any question, we can discuss about the chapters. All right, so who is in front of me? Nicholas Thomas. You're seriously thinking about. Okay. Nicholas, where do you go?
Hi.
I lost you.
Hello?
Yeah, I got it. Okay, I saw your video now. The question is like, what's the difference between high-level language and machine language? Just from your head, whatever you remember or understand. If not, you
Well,
said
I know that Java is a high-level language.
yeah, correct.
I don't know how to describe the difference between a high-level language and a low-level language.
Fine.
I think it has to do with the way the computer I guess it like translates the higher-level language into something
Yeah,
lower.
that's okay. That's okay. The first answer is correct. It has Java as an example for high-level languages. That's good. Good enough. Okay. Thank you. I'll go to the next person, so I don't have to spend a lot of time. Melody Long, are you there? Melody.
Yes.
So what's the difference between high-level and low-level or machine language in one sentence?
Machine language is mainly based on zeros and ones.
Correct.
While high-level language has more coding into it, like actual words and inputs and outputs and all that.
Okay. Okay, but I'll have more question on this though. Jill, are you here?
Yes.
So any definition of high-level language?
Like high-level language, I think it's basically used for like programmers and who can create complicated algorithms for the users. And I think low-level language is just uses in the fundamentals of like, I think it's binary one. And yeah, in the like fundamentals of computer, I think.
Yeah, you're just running in the bush. That's okay. You good try. Yeah, they're almost there, but not quite. Okay, Jonathan Burgess, are you there? Jonathan? Can you hear me, Jonathan? No, I think he can't hear me. Now, next name is popping up is Pragoti Makhani. Are you there? Pragoti Makhani. Are you here at all? Because then I'll take the attendance off if you're not here. I mean, if you don't know the answer, it's fine. There's nothing to go against you. Just say pass if you don't know. I don't mind at all. But if you're not here and you're still showing up in my screen, meaning that you just get attendance and disappeared.
Sorry, sir. I just didn't hear about myself. I just wanted to confirm I'm still present. Like, yeah, was my question anything?
No, I didn't call your name though.
Oh, okay. Sorry.
I called Pragati Makhani. And then before that, Jonathan Burgess. They're not here. They can't hear me, I think, in the bathroom or something.
Oh, yes, sir, I'm here.
Who?
Pragati? Yep.
Okay. So do you know what makes the high-level language?
What makes the
High-level language, like what is high-level language? How do you define it?
what is high
Say
level?
whatever you remember, or just say pass if you don't know.
I pass.
Yes, okay, that's fine, no problem. Now, Eric Rodriguez, are you there, Eric?
Yeah, I'm here.
Any idea? High-level language?
High-level language. I mean, I could probably like a binary code that a computer can probably use. But that's more of a low level.
No. That's okay. If you don't know answer, that's fine.
Alright.
You just pass. Christian Garcia. Sorry.
Yes.
Any idea about high-level language?
I'm not quite sure. I'd like to pass.
Okay, no problem. You're good. Stephen Pong.
Hi.
Yes.
So
High-level language.
so
Definition.
high level language is kind of like in English terms, I guess. And then the lower level languages is like, ones and zeros. And like simpler language, I guess.
Low-level language, they call it actually assembly language, not zeros and ones. Zeros and ones is actually a machine language. So high-level language is more like English-like language. Okay, it's English-like. That's the word. English-like, human, readable, and understandable language. It's very close to human language. It doesn't have to be English. I think other languages also can be high-level language. I think there are some coding in other language too. I heard of, but I never seen it. So it's more like human-like language, readable, and close to human language. You can understand if somebody reads code. That's the main difference. And of course, the machine language, on the other hand, is they use zeros and ones. And if you say low-level language, like assembly language, they use symbols. So that was the main difference we learn about high-level syntax. It says in the notes, it says English-like. So, and the assembly language is use symbols. Okay, that's the main, and machine language understood by the machine, it's only zeros and ones. All right, and another big difference in the high-level language and the other language, like assembly or machine language, is the portability. So your high-level language is more portable. Like if you write code in Java, you can run in any machine, which is in Java virtual machine. So it's very much portable. But if you write code in MIPS or assembly language, then it will not run other machines, only a specific one that you wrote for. Okay, and then the next question comes. Anybody have example of the reduced instruction set computers like RISC? Any example? You know, from your head? Anybody? Open question. So
Can
that
you repeat the question again?
is the example of the risk, like reduced instruction set computers. So we had two kind of instructions. One is complex instruction set computers and reduced instruction set computers, two sorts. So it's in the slides. And the example of the CICs, like the complex instruction set computers, is the desktops, laptops, and PS4, basically Intel x86. And the reduced instruction set computers, PowerPC, Apple Mac, IBM servers, MIPS, ARM processors. So there are the examples. It's in the slides, slide number 5, on the 0. All right, so that's the review kind of, and then we learn about servers, what is servers, and personal computers, supercomputers, embedded computers. So anybody has any, I think I should call somebody. Anish Katka, are you there? Anish?
Yes, I'm here.
Any understanding or example of embedded computers? Embedded.
I'm not quite sure, but I'm just gonna take a blind guess. Might be not the fancy, the Macs and the laptops, but it might be like calculators, like below computer versions. I'm not sure.
Embedded is not the calculators. Actually, it's computers in the cars and in other devices that you directly don't have actually interface, but you use it in the inside the machines. And also they have actually kind of the capacitors, like kind of local capacitors. Even sometimes you have a machine is running without any electric power, so it runs on battery. So they takes up like very little kind of battery power, so it can run as well. So programming those computers is a little different than laptops, desktop, or whatever devices we use. So most of the car, they have the embedded computers there. It doesn't have any direct interface. Because if you have a direct interface, then you need more power, basically. You have a monitor and all that, more power. So that's kind of example for embedded computers, like computers in the car and some other vehicle or other devices. And we learn about the cloud computing and software as a service. And I also mentioned another two service as well. So platform as a service and infrastructure as a service. So who remembers the example of platform as a service?
You said Amazon, right?
Yeah, Amazon is a platform as a service.
And is it Google is next, or there's like two, right?
Google could be platform as a service too, because they have Google Cloud and all other things. And the infrastructure as a service is more backbone-ish, like more larger scale, like road infrastructure or AT&T, like power infrastructure. Sorry, the telecom. The infrastructure, so people can actually rent their infrastructure and run their business on top of that. So that's the infrastructure as a service. So that's the kind of review we have. And then we covered a little bit input device, output device, all that, and integrated circuit. And then memory, we'll learn more about memory after. Volatile memory, non-volatile memory, and distance. So Another important one is the volatile and non-volatile memory. So let's go to somebody. Sean Nguyen, are you there?
Yeah.
Sean.
Yeah.
Remember the example of volatile memory?
Volatile memory?
Yeah.
Is that like RAM?
Correct. Is the correct answer. So the RAM is a volatile memory because once we turn off, whatever you typed in, your code and all that will disappear if you don't save in the hard disk or flash drive or anywhere. So that's the volatile. And non-volatile is your disk, your hard disk, your flash drive, your CD-ROM. Those are the non-volatile. When you turn off, your data is still there next time you turn on. So that's the main difference with the memory. But we learn more about memory in the later chapter, especially cache memory and also registers. So we'll learn about them very shortly. Okay, so let's look at the other chapter. I think we've been through the next chapter was the chapter 1. Yeah. We started learning about that. I think we stopped somewhere. So we learned the representation, signed and unsigned, and decimal to binary conversion thing. Anybody remember what we started? So did I show you the example in my board that how do you convert from binary to decimal, decimal to binary?
I think we went over that by you showing us how you just make 2 to the exponents and then making a table with that from 0 to 1, from right to left, and then putting like, I think depending on the number, we just see which one is subtractable from the table and then put a 1. And if it's not subtractable, you put 0 or something.
Good. So I showed you how to convert from decimal to binary in one method. There are 2 methods. So one method is using that chart that I think I still have it. Let's log into my OneNote. I'll share it. I think this is there. One example. Let me share. Yeah, so we gone through. I showed you how to convert a particular number like 194 to binary using this chart. So this chart is just kind of random arbitrary numbers. You just created 1, 2, 4, 8, 16, like double this number from right to left. And then that's equivalent to base 2 to the power 0 to the power 1, 2, 3, 4, like that. You can extend the table as long as you want on the left side. Like double the number, double the number, double the number, double the number. So keep going if you want to, if you have a big number to convert. But normally in terms of the IP address normally like 192, 194, that number starts with. So it's not very big because it's like 8 digits, 8-bit numbers, so cannot be that big. So this is 8-bit here. The highest number is 128 here. So, but if it is higher, you can extend your table and then use that. So that's one method to converting from binary to decimal. And decimal to binary and binary to decimal, you can use same table. That's the good thing. And this table, you can, the chart, whatever you call it, then you can use same chart to convert from binary to decimal and decimal to binary. See, binary to decimal is very easy. You just place your number underneath this chart, and then you see which one you used. You have 1, and you add them up together, and that will be the decimal. Whichever, like here, 128, we have 1 here, 64, we have 1, 2, we have 1. So add these 4 numbers, and that's your decimal number. On the other hand, for converting from decimal to binary, how do you do it? You split your number, the given number, in such a way that you can use this chart. So you split 194, like 128 plus 64 plus 2. And then you place 1 underneath that number that you used, and then rest you put 0, and that will be your binary number. Anybody has any question about this, understanding it? You have to be absolutely clear how this conversion works from binary to decimal and decimal to binary. Otherwise, we cannot move on to the next. We cannot proceed. We have to be absolutely clear, everyone. Anybody has any doubt? Then I can explain again and again, and show another example if you want. And then we move on to next step. Anybody has any question? I assume you understood it. Any question from the, I have 41 students here now. Everyone clear? If I ask you to convert one, can you do it? Yes, most of them say yes, 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 that's very good. If you are shy, you can type it. I'll go through it again maybe with another example, if you like, but you absolutely have to get this. All right, okay, next is, let's look at the next what we have gone through. So that's the, then we need to learn how to convert from hexadecimal to binary or decimal to hexadecimal. So binary to hexadecimal to decimal is really easier. Using the chart, you can do it. But the decimal to hexadecimal, there are of course two methods. One is splitting the number. So you create chart on 16 base 16. Am I sharing? So you split the number in such a way that you use the base 16, and then you just pick the coefficient of that base to the power whatever number it is. So it's like 131. That's your hexadecimal number, or 305 decimal number. So 305 hexadecimal is 131, and OX is actually just the stands for hexadecimal. You see OX, you'll see that the hexadecimal number. And hexadecimal number has been used for IP addresses, especially IP version 6 in networking. So that's why it's important to understand. And other one is this. You divide your number, given number, by 16, and then you pick the remainder. The quotient, whatever quotient it is, doesn't matter. Whatever remainder is, that's the matter. So keep the remainder, and then we go bottom up. 131. So OX 131 will be your hexadecimal number for 305 decimal number. So that's how you do hexadecimal to decimal to hexadecimal. Now once you have hex, if you use a 4-digit number, then it's easy to actually convert. You can convert back to binary.
Professor.
Yes.
So are we gonna take from the starting to bottom or bottom to starting, like for the converting decimal to hexadecimal?
If you divide by 2, then it's bottom up. So start from bottom and go up.
Okay.
Divide by 2 method. Even for binary, let's go through that one.
Yeah, for the binary, bottom to top. Yeah.
Yeah, same.
Oh, okay.
When you divide by 2 method, this is one. So divide by 2 method. So divide by 2, 124, remainder 1, divide 124, divide by 2, remainder 0, 62 divided by 2, remainder 0, 31 divided by 2, remainder 1, 15 divided by 2, remainder 1, 7 divided by 2, remainder 1, 3 divided by 2, remainder 1, 1 divided by 2, remainder 1. So this is how, then you go bottom up. If you like this, you can use this. I don't have any issue with that. But I like my chart method because I don't have to divide much like that. And I'm sure that I'm doing right. I can prove it.
Yeah, that's more like even the not time consuming too.
Yeah.
Time consuming as well. The chart method is better.
The second method is better?
No, first method, the chart one.
Yeah, if it is a small number, then you can do it quickly, very quickly. So that's why I like the chart method. And if you have given the binary, and converting decimal is very easy. You can use this kind of chart as here. So for 15 is 11, 1, 1, 1, 1. And then hexadecimal is F. And 14 is E, like that. So it starts from A, 10 is A, hexadecimal. You write it here probably, huh? I can write it here. No. Then I have to open up on the OneNote. So in let's open here, right over it. Then I can open. Maybe that will open a file. I think there is a way to open a file. I can't remember right now. It's okay. So for the binary. So the hexadecimal starts from like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's the, let's say that's the decimal number. And then hex is 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5, 6, 7, 8, 9. And then from 10, it starts with A, and then B, C, D, E, F. That's it. So that's the hexadecimal number format. 1 to 15 is like that. 1 to 9, and then A, B, C, D, E. So F means 15, E means 14, like that. And if you go binary, if you 4-digit, you can just write 0, 0, 0, 1, like that, and 2, 0, 0, 1, 0, 3, 0, 0, 1, 1, 4, 0, 1, 0, 0, 5, 0, 1, like that. So you keep going, and like F is 1, 1, 1, 1. Okay. So that chart there was yeah, this. And you can easily convert. Like if you see that, then you can, it's 0. This is 1. Like that. We have this 1011, you can just say 11 in decimal. And hex, you can say B. So it's converting from hexadecimal to binary is easy. Even decimal also easy. Binary also and decimal. So you can use this table. All right. So let's look at next. What do we have here? So now we learned how to convert from decimal to binary, binary to decimal, hexadecimal to decimal to hexadecimal, and hexadecimal to decimal. From this example. And so this is the method for the divide by 2 method, second method. It's on these slides, you can practice it. It's hexadecimal. OX stands for hex. Okay, now this is just a conversion from, so I said like the conversion from hexadecimal to binary is very easy because you can use that chart and do it. Here, OX5B3 is given. So 5 is 0101, B is 1011, 3 is 0011, like in 4-digit method. You just put it in here and that's the binary. That's the binary against this 5B3. And what is the decimal? Let's find out that. So it's 5B3 OX. So if you go OneNote, 5B3. So you have O, come on. We have X, 5B3. So that's our hexadecimal number. Now, how do you convert to decimal? So for decimal, use this 16 to the power 0, 3 plus 16 to the power 1 times b plus 16 to the power 2 times 5. So that will be equivalent to that. Now, this says 5 times 256, I think 16 times 16, plus b is 11 times 16 to the power 1 is 16, plus 16 to the power 0 is 1, so 3. Now, if you work it out, whatever it comes, okay, 5, 0, 3, carry 3, 25, 28, carry 2, 10, 14. Plus here 16, 6, carry 1, 16, plus 1, 17, I think. So whatever it comes when you add it up, 9, 15, carry 1, 2, 6, 1. So that's the decimal number for this x. And binary is equivalent to, if you put a binary equivalent, it's very easy. So you have 3 is, if you use 4 digits, 3 is 0, 1, 1, and b is 11. So 11 is 1, 0, 0, 0, 1, 1 from the table. B 1, 0, 1, 1, correct. And so I put 1, 0, 1, 1 here, and 5 is 0, 0, 1. So that's the binary equivalent to this. So this is hexadecimal, binary, decimal, same number. Clear? So if we have hexadecimal, binary is very easy. Just use this chart and just put it there. And if you have bind and hexadecimal, you have to do decimal, you have to do 16 to the 0 base, and then you get the decimal. And if you decimal, then you use chart for 16 base, or you just divide by 16 and take the remainder from bottom up. All right? Okay, let's move on. So yeah, we'll be reviewing that in the next class as well, like how you can convert this system. Okay, octal is not very popular, but I still need to learn it. I think sometimes you see views of this. So octal is base 8. So all the system is same. You create chart for base 8, or you divide by 8 and take the remainder from bottom up. Same rules. But yeah, you can do it yourself. It's not a big deal there. I use 3-bit unsigned and signed numbers. So if you don't have any sign, that means it's unsigned numbers. If you're given a sign, so that's the signed numbers. Now we learn how to do addition and binary numbers and hexadecimal numbers. So look at this numbers. So we have 0, 1, 1, 0 and 0, 0, 1, 1. Let's go to the OneNote. 0, 1, 1, 0. So we have 0, 1, 1, 0. And the other one, 0, 0, 1, 1. So you write 0, 0, 1. Basically, this is 2. All right, so this is 2 numbers, so you're going to addition here, so put a plus sign. So it's a normal decimal number where you start from right side, same here too. Start from right side. So what is this number? 0, 1, 1, 0 in decimal.
6.
6. And what is this number? 3. respecting 9, isn't it? So here we'll see the same. So 1 plus 0, 1 plus 0 is 1. So I put the 1 here, no carry. 1 plus 1 is actually 2. So 2 is in binary, you write 1, 0. So you put a 0 there and you carry 1 actually in your hand. So then 0 plus 0 is 0, plus 1 is 1. Oh, sorry. Put a 0, then 1. So then the next is 1. So 1 plus 1 is 2, so it's 1, 0. So you put 0 there and carry 1, and then 0 plus 1 is 1, and 1 plus 1 again, 1, 0. So you put a 0 here, and then carry 1, but then 0 plus 1 is 1, 1 plus 0 is still 1. So put 1 there. So this is 9. So you can do it, you can work it out as a base 2. So 2 to the power 0 plus 0 times 2 to the power 1 plus 0 times 2 to the power 2 plus 1 times 2 to the power 3. So that should be this equivalent to that. So 2 to the power 3 is 8 plus this is 0, this is 0, this is 1, so it's 1, so it's 9. So it's correct. So this answer is correct. I proved it. So it's 9. And it's supposed to be 9. When you do the decimal, 9. Same thing. So you notice that like when you add 1 plus 1, that's 2, but you don't put 2 here because it's binary. Binary 2 is 1, 0. So you put a 0 there and then carry 1 to the next. So 1 plus 0 is 1, and then 1 plus 1 is 2 again. So that's 1, 0. You can just put 1, 0 here, whereas the last 2 digits is 0, 0. So it doesn't matter. It's 0, 0. It's 0 plus 0 is 0. So you don't get anything. So 0 plus 0 is 0, and carry 1 plus 1 is 1. So 0 plus 0 plus 1 is 1. So that's why it's 1, 0, 0, 1. Any question? So this is how you'll be doing your binary addition. Whenever you have like 1 plus 1, because it's number 0 and 1, nothing else could be there. So when 1 plus 0 is 1, and 1 plus 1 is 2, but 2 is 1, 0 in binary. So you put 0 there and carry 1 like that. Simple. Now we go back to the hexadecimal. It's more interesting. Hexadecimal addition. So I have 3DE. Go back there. 3D 782. Hexadecimal. So we go 3DE and 282. 282 or 482. 782. 3DE and 782. Actually, you don't write in capital. X thing. You don't write in capital, write in small. So DE and 482, 782, 782, 782. Because in hexadecimal, 7 is 7, 8 is 8, 2 is 2. Only the 10, 11, 12, 13, 14, 15 is A, B, C, D, E, F. All right, now here is the tricks. Because here, if we carry 1, that will be 16. So that's the thing. So the E, A, B, C, D, E, A, B, C, D, E, this what? 10, 11, 12, 13, 14. So the E, basically 14. So E minus 2, sorry, doing addition or multiplication? I think we're doing addition. Hey, we're doing addition. Then we add 2 there. So now the trick. So add 2, then we become 16. Now, 16 is...
I have a question.
Yeah.
How is E14?
Oh, E14 because of this chart that I show you that. After A, it goes here.
Okay. Is that binary?
14 is E, hexadecimal.
Okay.
14 is E. 14 is equivalent to E. Actually, as I mentioned, this should be small letter, not the capital letter. A, B, C, D, E, F. So 15 is F in hexadecimal. So since we're doing hexadecimal addition. So this 3DE, they're in hex form. And hex form, like 1 to 9 is still same as decimal, like simple, but the hex, the base 16. So now the base 16, so you got 1, actually it's 1 here, but you don't need to put 1 here because you can take the 1 in this side because it's a whole 16 base. So you put a 0 there. So that's kind of surprise. So you put a 0 there, not 16. Because you take 1 as a whole number, you take carry with this. So this 1 is there, and you add D to 1. So the D is what? A, B, C, D. 10, 11, 12, 13. So D is equivalent to 13, plus you add the carry 1. So you have 14, plus you add the 8. 8 says 22. So 17, 18, 19, 20, 21, 22, 6. So you left 6 here. So 22, you can split as 16 plus 6. So your remainder kind of 6 here, and 16 will base 16, so we have one whole number that will go to the next. So you carry 1 here, and then you carry 1 here. And at 6, you put 6 here. So you carry 1 here. Now you add the 3 plus 1 is 4. 4 plus 7 is 11. 11 is B. So this is your result. It's kind of weird, but that's how you do it. When you have 16, you take a carry 1. And because 16 plus 0 is 16, so you put 0 there. The first one we have 16 here. So 16, you can split 16 plus 0. So you put a 0 here, and 16 will carry 1, and that's 1 here. So then you add D plus 1. D is 13, so plus D 13 or 14. A, B, C, D, 10, 11, 12. Yeah, 13 plus 1, so it's 14. And then 8, this 8. Then you put 8 there, so 22. 22, you can write 16 plus 6. So 6 goes there, and 16 carry 1 there, 1 here. And then you add 3 plus 1 is 4. 4 plus 7 is 11. 11 stands for B. So this is the B. So this is the result of your addition, hexadecimal addition. Any question?
Professor?
Yep.
I'm still having a hard time understanding how 16 became 1 and 0, or what we do with 16. Could you explain that one more time? I'm sorry.
Yeah, sure. So we are doing hexadecimal addition. Remember that. Hexadecimal means base 16. Base 16. So when we do normal, let me give an example here. For the decimal example, it's similar. Okay, let's say we have a decimal number, so 1, 8, and 3, 5. Okay, that's the decimal number that we use normally, decimal number. So base 10. So 8 plus 5, what? 13, isn't it? So we put 13 and 3 there, and then we carry 1, isn't it? So we carry 1, and then 1 plus 1 is 2, and 3 plus 2 is 5. So we write this, 5, 3. So you want to carry 1, because it's a decimal. So so it's actually 13, but we don't write 13 here, because we can write only 1 digit. So we put a 3 there, and then 1, we take it as a carry, and then we put it on the top, and then we add to the other number. 1 plus 1, 2, and then 3 plus 2, 5. Correct? In the decimal, you're correct there?
Yes.
Very same way we're doing this hexadecimal. So since E plus 2 is actually 16, we cannot put 16 because 16 is a 2 digit, isn't it? It's 2 digit. So you cannot put 2 digit there. So we have to put 1 digit and carry 1. So 16 is a hexadecimal. So it's basically, if you move to the next, that will become 1. And then 16, we can break it like 16 plus 0. So that's why I put 0 there. And carry 1 there. This is 16 actually. This carry 1 means this is 16. So then now you add 16 plus D. So D is 13. Sorry, not 13. What's the D? A, B, C, D, 10, 11, 12. Yeah, 13. So D is 13, and then you add the carry 1 with that, so that's 14, and plus 8. So it's 22. So 22, but you can't put 22 there because you put 1 digit there. So you split 22, 16 plus 6. So you put 6 there, and 16 is your carry because that's the base. Here, we took 1 as a carry because it's actually 13. So 1 is the 10th position. Here, 16th position. So we base 16, so we take as 1 as a carry. That's why 16 plus D is 13 plus 1. So 1 plus D is 13 plus 1, 14 plus 8 is 22. 22, we can split 16 plus 6. So we put 6 down there and 16 as a carry. So we put 1 here, carry. And then 3 plus 1, 4. 7 plus 4 is 11. So 11 equivalent in hexadecimal is B. So the result will be B60. 3DE plus 782. Result is B60. So that's the hexadecimal.
Thank you.
You know that? You can double check it. You can double check it. You can convert this to decimal and convert this. This is actually in decimal, but you can convert this to decimal too, and then add them up. Then you can convert this to decimal and see if the result is equivalent or not. So this is, you can prove it. The addition is correct or not. You can convert this to decimal, convert decimal, you add this to up, equivalent to this should be. If it is, then your answer is correct. So as soon as you get 16, then you split the 16 and carry 1. And the rest you put it there. Because you cannot put 16 there. 16 is a two digit. You cannot put 2 digits there, so you put 1 digit. Because you know that after 15, we don't have the hexadecimal number. Like here, that's why. The next one, I put this out here. Here, you see that after 15, decimal 15, we don't have any hexadecimal. It's finished. F. F is the last number for hexadecimal. There is no other number. There is no next 16, 17, 18 is not hexadecimal number. You cannot represent that. Because as soon as you get 16, then that's the base 16, so you can carry 1. That's why you don't need after that any number. So as the decimal number, after 9, after 10, you don't need any number. After 10, you don't need a number because then you can write it by the tenths. 10 plus 1, 10 plus 2, 10 plus 3, 10 plus 4, 10 plus 5. You can write forever. So because base 10, we don't need any number after 10 actually. So you can get by with this when you write up to 100. Up to 9, 10, that's it. You don't need up to that. 9 actually, then you don't need after that number. So 16, base 16, so up to 15, and then after that, you don't have any other number to represent. So you just carry, as soon as you're 16, you carry that over, and then whatever over, like left over, you put that number there. It looks different, but that's how it is. All right, so now look at the next. Unsigned integer subtraction. So now, how do you do this binary subtraction? With binary number, we learn how to do the addition, but how to do this subtraction? There's a similar way, but then if you get a number 2, then it becomes 1, 0. Or
I actually have a quick question.
Yep, sure.
Because you said that if we get 16, we can carry the 1.
Yeah.
But then if we have like 13 from the example you made, can we not just use 13 as one of the letters? Do we have to carry? Do we have to make it like 1 and then carry the 1 and then remainders of 3?
Yeah, we could, but then we don't have 13. We have actually 22.
Oh, I'm talking about the one you did for 18 plus 35, and then you got 13, so you got 3, and then you carry the 1 on the left.
No. Which one? This one?
Oh no, bottom left.
Second one.
No, that's the one that you were giving us as like example of 18 plus 35.
Oh, that's the decimal.
Oh, Oh, okay.
That's the normal math we use.
Oh, okay, okay.
General mathematics. Example, I showed you that actually a similar way we're doing this, but this is, since this is a 10th, we call it decimal. So 10 base 10. So that's why we take 1 as a carry and then do it.
Oh, okay. So basically, if it's like less than 16, we still can just use like a letter instead, right?
Exactly. That's what I did here.
Yeah.
See,
Yeah.
11.
Okay.
So we got 3 plus 1, 4 plus 7, 11. We put B there.
I see that now. Yeah.
Yeah, that's actually 13. Because 13, we need 2 digits, but the hexadecimal 13 is 1 digit, is B. So you just put B there. You got it now?
Yeah, I got it. Yeah.
Anybody has any other question? I'm happy to go over again and again, because it's a simple concept, but since we are not familiar with this hexadecimal addition, subtraction, that's why we need to go over it. I'm happy to do that. It's not a problem. But it's very simple. Is if it is base 16, then as soon as you get a 16, then you don't put 16 there, you put 0 there. If you have more than 16, then you put that. If it is 17, then we put 1 there and 16 carry over 1. So if the first here, instead of E, if we have F, for example, then we have 17. 15 plus 2, 17. 17 is 16 plus 1. Then instead of 0, we put 1 here and then carry 1 there. You get that?
So it's basically just looking for the remainder of if we could get 16. Yeah.
Yeah, remainder. So let's say this 3DF this time. That's why we have same at the bottom. Now, if we want to add this, so F is 15. So the 15 plus 2 is 17. The 17, we can split 17 by 16 plus 1. Then we put 1 here and carry 1 here. And then we'll have, so the D is 13 plus 1, 14 plus 8. So 14 plus 8 is 22 again. And then exactly the same thing. So then we have 20, so 22 here. Then we put 6 here and 1 remainder. And then 3 plus 1 is 4, 11 plus B. So now it will be B.
B61. Yeah.
6-1. B61. Yeah, 6. The 6-1 instead of B60. Because we changed the number from E to F. So go one higher. So we go one more extra. So this is how you do your hexadecimal addition. Even instead of 8, 7, 2, if you have like C, A, B, same way, you just convert to decimal and then add them up, and then you split it by 16, and then whatever remainder, you put the remainder there and take 16 carry on the top. Okay, so that's an example for hexadecimal addition. Now, subtraction. We learn subtraction now. So let's use the same example, 10, 10, and 1, 0, 1, 1, 0, 1, 0, 0. Let's go there. Okay. So we have 10, 10. What the other one was? 0, 1, 0, 0. 0, 1, 0. So this is 4. This is 10, I think. This is 10 and this is 4. So we do subtraction here, not addition. How do you do it? So let's say we have 10, this is 10, and 3 is 10, 8 plus 2. And this is 0 to the 1 to the 2. It's 4. So then you're expecting 6 here. We deduct it. All right, so now how do you do it? Same thing. We in general mathematics, like base 10, what do? We get the top number and then compare to the bottom number and put the difference. So here we have 0 minus 0 is 0. And then we have 1 minus 0. 1 minus 0 is 1. Isn't it? So 1 minus 0 is 1. Now, 0 minus 1, you cannot do 0 minus 1 because 0 is smaller. So you have to borrow from from the left side, 1. So that's 1, 0. Now it becomes 2. So if it is 2, so 2 minus 1 is 1. Okay? So then you borrowed 1, so you take the borrow here, put it here, for example. And then 1 minus 1 is 0, so just put 0, it's no point, right? Because 1 is, you can do 1 minus 1, but you cannot do 0 minus 1. So 0 minus 1 is just so you borrow 1, so it becomes 1, 0. So that is basically 2. The 2 minus 1 is 1. And then you take that, borrow 1 back here. And then 1 minus 1 is 0, just put 0 there. So it's basically 6. So this is 6. That's correct. That's it. So that they put 2 there to show you that is 1, 0 is 2, 2 minus 1 is 1. And then 0 minus 1 is 0. 1 minus 0, 0 minus 1 minus 1 is 0 actually. So it should be that, not like this, 2, whatever. So this is how you do this binary subtraction. We can see this example as well, bigger one. 0, 1, 0, 0, 1, 0, 1, 1. We can try some other example. Did you get this one? This...
Can we try a smaller number?
Huh?
I think this number is a bit too big for me to, because I know that you can convert it to 10 and 4, and then we get 6. But I'm still confused of how you do like the subtraction without converting them into like integers.
Yeah, this is I'm showing you the proof that is.
Yeah.
So let's say this is what 2. 1 0 1 0 0 1 0 is 2. In binary is this. In decimal is 2 basically. So if you deduct 1, I mean, this is very simple then. So now here, 0 minus 1, you cannot do it because 0 is smaller. So you borrow on the left side from one number. So you take 1. So now 1 0 becomes 2. So 2 minus 1 is, so 2 minus 1 here, 2 minus 1 will be 1. And then you borrowed that number here, so you put it here. Then 1 minus 1 becomes 0. So this 0 there, 0, 0. So this is 1. And it's correct. 2 minus 1 is 1. This is binary 2, this is binary 1. I just put 4 digits, doesn't matter. You can put 2 digits as well, like this. Still 2 and 1 in binary. So you can do the same thing. So 0 minus 1, you cannot do it. So you borrow 1 from here, it becomes 2. So 2 minus 1 is 1. And that's it. 0.
Oh, so basically if it's a 0 and when we take a number on the left, which is a 1, it becomes 2 because it's basically, we consider 0 as 1. So it'll be 1 plus 1 is 2 and then 2 minus 1 will be 1, right?
Yeah. So it becomes 2. When you borrow this 1, it becomes 2.
Okay.
This 1 is 1.
And
if you say, okay, if you take the borrow here back, then it becomes 1 here, and then 1 minus 1 is 0, so it's just put 0. Doesn't matter.
Okay.
So that's the binary subtraction. It doesn't matter how big the number is. As soon as you follow the rules, then it should be fine. Binary subtraction. Okay, well, not today. All right, so focus on this. And I'll go through it again. We have time, we can go slow, it's not a problem, we're not in a rush. So we have plenty of time.
I got a question.
Yes.
Is there any other way for us to like learn more about this, or is it just reviewing the slide over and over again until we understand it?
No, you should practice.
Oh, okay.
Practice more, you should practice more. Just make up a number and just practice it.
Okay.
We'll do more practice. I'll give you homework as well. So homework will come after end of this week, I think. After the next class, I'll give you homework for the conversion. Binary to decimal, decimal to binary, decimal to hexadecimal, hexadecimal to binary, and binary subtraction, binary addition. That's it. So we'll have a homework like this. Then you practice and do more homework. Should be fine.
Okay, thank you.
As soon as you get the concept, I mean, some of it probably, a lot of you probably know it, But if you don't know it, it's fine. You just learn it now, okay? Because this is essential as a computer scientist, essential to understand how actually computer works, how computer does the calculation in the ALU unit, like arithmetic logic unit, how this calculation happens. Using this 0 as 1, 0 and 1, they're doing a lot of complex mathematics, isn't it? A lot of complex calculation just using zeros and ones, like on and off switch. So that's why it's pretty important concept to understand how this works. And then that's how actually computer uses switch on and off switch to do this sophisticated calculation. We'll see how it works in different gates, and when we go through the logic gate and also the truth table stuff, and we'll see. It's interesting, very interesting that how people thought this clever way to solve like larger problem just using 0 and 1. Because that's the only thing you can do. You have a light, either it's off or on. So that's the two things you can do, two state. And that using two state, there's a lot of sophisticated calculation, you see that. So whatever you do in computers, it gets converted to 0 and 1, and then you save to the disk. And CPU only understand that 0 and 1, nothing else. So it's very interesting, and if you get it, it's good. It will be useful for your future career actually. So that's the and that's the class today. I think we'll stop here. We go slow, but I want you to get it clear that you get this. This is very basic, computer science stuff for this course, computer architecture. That's why once you understand this, then you can actually represent very complex number and design a CPU to calculate that. You will be a designer of CPU. How do you come up with new computers? Once you learn these tricks, how to represent a number, complex number, large number, then you can use it. And decimal number 2, floating point number. We'll learn about that floating point number in the end. All right. So I think we end the time. So we'll go through it again, review it again, look through all these slides and examples I mentioned, and we'll go from there. Next class.
Professor, I had a question about the homework.
Sure.
Is it just going to be worksheets that you send us through iLearn, or is it going to be through another website?
No, that's through the iLearn.
Okay.
Everything will put in the iLearn. So once it's ready, I'll let you know, and you check iLearn every day and you'll see it is there. And then
Okay,
you
sounds
download
good.
that. You download that PDF file, and then you work on it, and then make a PDF and upload it.
Okay.
If you are new to the iLearn, but if you're not new, then you know it, how iLearn works. Okay. Yeah,
Thanks,
let me
Professor.
know. Let me know if you have any issue. If you're new, like transfer students, you're not familiar with iLearn, then I can help you with that too. No problem. All right. Take care. See you in the next class.